Okay. There we are. Welcome to the gateway. Let's do this. That screen recording's a little obscene. There it is. Big, fun stuff. I'm going to whip through this gateway and think of everything that's on this gateway, the question types for all the multiple copies that I have of this. Remember, you have to get 90%. So if you miss two, you're good. If you miss any more, you have to take it again. That's really frustrating. I know it is. You miss three, then that's just annoying, especially if you've done it a couple of times. The idea is you'll get full credit for passing if you do miss up to two or less. On the 7th copy, it looks just like this. It's just different versions of Dirty Dozen functions and all these little manipulations, asking about end behavior and stuff like that. So they just change ever so much. The questions are the same, the functions change. So let me go through and make sure you got clarity on all of this. Like, state the domain of y equals x. It could be the domain of any function. So backing them up. I'm making little markings here. Come on, buddy. So the domain of that number 1, y equals x, all real numbers. You could write all real, but I'm going to do all interval notation today just to give you the heads up on that. Then, of course, what's the range of y equals x squared? I'll give you a hint. It starts with a bracket. Where's x squared start range-wise? 0. Goes to infinity. So that's it. Some of them are really straightforward. Depending on the Dirty Dozen function you're talking about, you can write in other fashions. It's okay. Do you need a copy, Rachel, by any chance? That. The gateway from yesterday. It is behind you. It's over. Anyone else too? It's behind the pinky sheets over there on the table. Anyone else need one? This will give you a sense of what to expect before you take it yourself. Yeah, it should be the gateway thing. Nope. Maybe I took them off. Okay. Ooh, I've got some up here. Come on up here. Here you go. There you go. Anyone else need one of those? Yeah. If you didn't get one yesterday, that's fine. But you'll want one now. There it is. So if you do domain, negative infinity to infinity, you could have said all real numbers. That's fine. Range, you can also, honest to goodness, if you're talking about range, I like this personally better. I just know how important interval notation is, so that's why we use it. It ends up being important later. But don't you like just y greater than or equal to 0? Doesn't that say nice? Range is way clearer. It tells you also it's a y value. So live with that. If that makes your comprehension go up, do it. State the intercepts of the function radical x. Now, depending on what Dirty Dozen function we're talking about, intercepts are where it crosses the x-axis. This crosses at 0, 0. So we go 0, 0. No big deal. Okay, and then we go to like end behavior of x cubed. That does throw a few of us off. We got to talk about end behavior. It means to look at literally the ends of the graph, and we describe it by saying, all right, as x goes to one end, what does y do? I mean, that is, what does the height of the function go to? So there's two ends to this graph. So you go as x goes to infinity would be the right end behavior. Then what does y do? Well, y goes to infinity. So there's one end, the right end. The left end of this graph is as x goes to negative infinity, y goes to negative infinity. You're describing the height way, way, way down there. Sorry, I need the negative in there. So that's end behavior. It depends on how many ends you have. An end can be a point, which we saw earlier on this year. Intervals of increase and decrease. Get a sense that I'm going to ask these same questions, different functions. So intervals of increase and decrease, you got to know these crazy functions. Like 1 over x, you just got to know that thing. I mean, in your sleep, you're dreaming about 1 over x functions like this, like this. And if I say increase or decrease, I hope you got the sense of you're looking at that going, when am I going uphill? When am I going downhill? Looks like if I got on here and skied, that's always going downhill. If I got on this slope and skied, I'd always be going downhill. You read left to right, so it's always going downhill. I'm going to put it off just right here on the side. It increases never, and it decreases, well, everywhere but 0. And you could write everywhere but 0. But I would prefer, the thing you have to know is how to write that in interval notation, with the union thing, 0 to infinity. Okay. Doesn't that look like we're just reciting things from the Dirty Dozen sheet that I gave you? You noticing that? It's basically being able to recollect those in this context. Then there's asymptotes. Absolute value of x. I have a habit of drawing the function every time one of them comes up, because then it's easy to answer the questions. Are there any places this graph hugs? Does it like snug up against some kind of line? Does it bend down and get as close as possible without even touching? That's an asymptote. And this one's no, there's no asymptotes. So you'd write none here and on the space. It's not y equals 0. Just because it goes to 0 and stops, that's not an asymptote. You're not snuggling up against there and getting that awkward warmth that made us all tingle that day that we performed function asymptote stuff. Okay. And is there an inverse of sine of x? No, doesn't exist. And let me show you why. If you actually did the inverse of sine of x, it would look like this. Kind of up and down the curve there. And that doesn't pass the vertical line test. And we talked about that. That's on the Dirty Dozen. Yes, someday Mr. Seeley's going to say, hey, let's do the inverse sine. And you'll say, but Mr. Seeley doesn't exist. Well, when I say it later on, I mean only the limited version from negative pi over 2 to pi over 2. I mean a small chunk of it. We do inverses limitedly. Symmetry for tangent of x means you got to graph probably and take a look. There's tangent. It's got those asymptotes. Pi over 2, negative pi over 2. The symmetry on this dude, odd. Odd symmetry. Symmetry about the origin. It's odd. It's odd. Tyler, you are so full of information today.
I'm sorry, there's a girl that's, she's a junior here, and she's getting married.
Really?
I just can't get over that.
Wow.
I literally got proposed to.
Now, is it going to be like a married?
Like married, like, yeah. Like,
Well, I hope you all get married someday. It's a wonderful thing. It's beautiful. Oh, you mean like?
imagine if you were her parent. What would you do if you find out that your daughter who's 16 just got proposed to?
That's just
No.
no. Just not no.
Yeah,
It just no. You can pretend you said yes, but no, you can't. You're right. You put me. That's not fair. You put me in dad mode. That's a different answer. All right. Here's y equals e to the x. It says asymptotes for that. Oh yeah. There's huggage. So look. Maybe what happened is that this poor girl, I don't know, they were just getting a little too close. A little too far out there on the asymptote. But they never touched, I'm sure. Never touched. But got really, really close. They just really enjoy each other's personalities. Planning a wedding for the year 2017. Let's be optimistic. Okay, y equals 0. Natural log of x, odd, even, or neither. Oh, I'd go with neither. Definitely neither. But we'll write neither. It's easier to write neither and say neither. Have you noticed that? There you go. Any questions on that top part? You see it's knowing the Dirty Dozen on the top. Down below, it's transformations of the Dirty Dozen. And I'm going to show you my technique. It may not be your favorite, but my technique is, I don't know, it might help some of you. So why don't you do this? I'm going to take this graph, do it in the grid here. I'm sorry for how tiny it is on your sheet. When you get an actual gateway, it's a full-size sheet on each side. So it's not as tiny as it is on there. So do your best to kind of hang in there. I'm actually going to graph the original. So I want you to know what the radical x function looks like. It goes through 0, 0. It also goes through 1, 1. I think that's a bare minimum. You should be able to do 0, 0, and 1, 1 and graph it from there. You know that if you put 4 into radical x, you get out 2. Maybe you want to do that. But that's the shape. There you go. That's radical x. Radical x plus 3 is, as you know, means go left 3. So I take that thing over here. 3 spaces, still go over up 1 over 1. And I still go over 4 up 2 and just trace it out that way. I like to draw the original and then do the transformation sometimes because it helps me see how it changed. You don't have to. This is all I need to see. I just need to see the resultant function. Ugh, that word is killing me. Function. Can't get that right. Moving on. I got this one. Let's do a little pinkage on the original. So e to the x is, we just talked about, right there. E to the x. And it just takes off like that. Now, this transformation, e to the negative x, has a couple of them. You want to start with this one, that negative. Ooh, that's something. Negative x, horizontal flip. Plus 2, let's do a different color, up 2. Okay, so we'll go back and tackle those. The horizontal flip, to do that, you just literally rotate it about the y-axis, so you turn it around. Like that. My wife's sang that song the other day in front of her students. Turn around, every now and then I get a little bit. You know what song I'm talking about? Something like that. Turn around. Then it gets to the chorus. It's like, turn around, bright eyes. Every now and then I fall apart. Well, she started singing part of that. First grader finishes the song. Isn't that cool? So a first grader knew this one. This is e to the negative x, by the way. That's just the horizontal flip. Then, now we're talking seriousness. The final thing, the up 2, you take that negative x one, the flipped one, go up 2 spaces, wha-bam. Now you have to keep the asymptote in the right place. Okay, so the horizontal asymptote used to be 0, but now it's up here at y equals 2 because I shifted it up 2. So this is the one I'm going for. So the final version is this, the one in this, shall we call that, yesterday, blue, teal, light blue. Somebody said, we talked about the color of my shirt yesterday, and we decided it was seafoam. Seafoam. Good. Moving on. Bring me back to anything. My favorite one. Let's go talk sine of x. All right, I'm going to do it in red because it's muy importante. This, let's say this is 1 and negative 1. It is way too small to try and squeeze sine into this mini grid that you have. I know it is. Make pi right there. And 2 pi right there. You may not remember your sine very well, but you will. Sine goes up, down. This is regular sine. Like that. Up and down and up and down. Y'all know that sine of x and cosine of x go between -1 and 1, like you see here. And one full iteration, 0 to 2 pi. So you got a whole sine curve. It goes on forever, but I'm just graphing one little piece. That's sine of x in red. Good to know that. Now to do the transformations it calls for in this one, I'm going to show you a way that you don't actually have to draw all these. You can actually just manipulate the parameters of this, like the size of it. Okay, so for instance, see that 2? Y'all know that's going to make it twice as tall. It's a vertical stretch, and you know this one, so that's v stretch by 2. And that pi over 2, that means right pi over 2. I am actually not going to do any moving of this graph. What I'm going to do is show you that if I double this vertically, stretch this thing vertically, what are the peaks going to go to? What is the valley going to go to if I double it vertically? Yeah, 2 and what else? -2. 2 and -2. That's it. If I currently go 1 and -1, if I